these two are slightly different because a GPU needs a little bit more space than, say, a couple.
You are Cell.
Throw versus Anduin.
Maths, science and computer science. Mars is a disappointing hellhole lacking practically everything we need to stay alive. It looks like we'll only ever have small crews spend a miserable time hidden underground. Except we could terraform it into a green new world. But to solve the planet's problems, we first need to make it worse and turn it into oceans of lava with gigantic lasers. This isn't a far-fetched science fiction tale. Terraforming Mars is possible on the kind of timescale our ancestors built great monuments in. If humanity solves some of its pressing problems and ventures into space to expand into the solar system, this may not be that far off. Okay, so how do we terraform Mars quickly? Well, it's complicated. Mars is dry and has no soil to grow anything. Its atmosphere is too thin to breathe or protect us from radiation, giving you a high risk of cancer. So to turn it into a new home for humanity, we have to give it a proper atmosphere similar to Earth's. It should be made of 21% oxygen, 79% nitrogen, and a tiny bit of CO2, at an average temperature of 14 degrees Celsius and under 1 bar of pressure. We have to create oceans and rivers, and then the ground has to be weathered into fertile soil to host living things. Then we need to install a biosphere on the surface and prevent it all from being undone by installing protective measures that can stand the test of time. It is difficult, but a big laser makes it a lot easier. Challenge 1: the atmosphere. Some 4 billion years ago, Mars had a nice oxygen-rich atmosphere and was home to vast oceans and rivers. It held onto it for several hundred million years before it got blown away. Ultraviolet rays broke down the atmospheric gases and then the oceans until they were swept away by solar wind. Today, Mars is a dry, barren wasteland. Luckily, a sizable portion of the water is frozen in deep reservoirs and in the polar ice caps, enough to create a very shallow ocean. And enormous amounts of oxygen are bound as minerals in the Martian rocks, like the oxygen in the iron oxides that give the planet its rust-red color, as well as carbon dioxide in carbonates. To free these gases, we need to reverse the reactions that lock them away by using thermolysis, which occurs at temperatures as high as on the surface of the Sun. In short, we want to melt the surface of Mars. The best way to do that would be to put lasers in orbit, aiming their beams down on Mars. The most powerful laser today is the Eli NP, able to produce beams of 10 petawatts of power for a trillionth of a second. To melt Mars, we need a laser twice as powerful that runs continuously. The easiest way is to use a solar-pumped laser that can be powered directly with sunlight. At its core are metal-infused glass rods that absorb energy and release it as a laser beam. If we build an array of mirrors in space about 11 times the size of the United States, we can focus enough sunlight onto them to melt Mars. Let's do it. As the lasers hit the surface, about 750 kilograms of oxygen and some carbon dioxide emerge from every cubic meter of rock melted. If we are efficient, our lasers only need to melt through the top 8 meters of the surface to get enough oxygen. It would look terrifying. The skies would be shrouded in storms, while the ground would glow red-hot, crisscrossed by currents of lava. Tireless laser beams sweep over the landscape, leaving trails too bright to look at. After they pass, the ground cools quickly. A strange snow falls, the ashes from all the elements that solidify as they cool down, like silicon and iron. Mars is still a cold planet at this point. A happy side effect of this inferno is that all the water in the polar ice caps and even deep underground rises into the sky as hot steam, forming clouds that rain down over the entire planet. They would wash out the nastier gases from the atmosphere like chlorine and carry away harmful elements that accumulated on the surface. In the end, they would form shallow oceans, saltier than on Earth. We might need to do an extra cleanup afterwards. It would take about 50 years of continuous lasering to create our oxygen atmosphere. We could use this opportunity to dig deeper in some places to create the basins for salty oceans or rivers and spare some landmark features like Olympus Mons and Valles Marineris. We're not done though. The resulting atmosphere is nearly 100% oxygen and only 0.2 bar. It's hard to breathe and very flammable. To make it similar to Earth and a lot safer, we need to add a lot of nitrogen, which Mars is sadly lacking. We have to import it. The ideal source is Titan, a large moon of Saturn, covered in a thick atmosphere that's almost entirely nitrogen. We just have to move 3,000 trillion tons from the outer solar system to Mars. While that's not easy, it is doable. To process that much of Titan's atmosphere, we have to construct giant automated factories on its surface powered by our lasers to suck in the atmosphere and compress it into a liquid. This gets pumped into bullet-shaped tanks, which a mass driver shoots all the way to the red planet, where they explode and mix with the oxygen. We've already been able to send individual missions to Saturn in just a few years. With enough resources, it should be possible to complete the task within 2 generations. Of course, it would be much more convenient to have nitrogen left over from terraforming Venus on the side. We explained this in detail in another video. So, about a century after the start of the terraforming process, we have a breathable atmosphere that has the right gases. If the liberated CO2 isn't enough to warm it up to temperatures we can stand, we just add some super greenhouse gases. Mars at this point resembles a black marble from all the cooling lava, spotted with growing oceans and red patches where the old surface remains untouched. It's still a wasteland, no better than a desert on Earth. We need to fill it with life. Challenge 2. Biosphere. Installing a biosphere on a new planet is very difficult. Unexpected interactions between species or sudden diseases can destabilize it to the point of collapse. We would probably begin by seeding our young oceans with phytoplankton. Without competition, it would bloom rapidly, filling up the oceans to become the bottom of an aquatic food chain. They can be followed by tiny zooplankton, then by fish, maybe even sharks and whales. If things go well, life in the oceans will thrive. Life on land is harder. Plants need nutrient-filled ground to sink their roots into, but most of the surface is the congealed remains of lava and ash. We could wait for thousands of years for water and wind to grind it down into finer sands, or try to do it manually. But we want to be quick, and we have a big laser. Turning the beam on and off in rapid succession would cause the ground to quickly heat up and contract, which breaks it into smaller and smaller pieces. Add a bit of water and you get a sort of dark mud. Into this mud, we can mix fungi and nitrogen-fixing bacteria. They're able to absorb nitrogen and convert it into nitrate compounds to feed plants. The first plants we want to bring are native to volcanic islands on Earth, since they're perfectly suited to the laser-blasted Martian landscape. Eventually, the enriched mud becomes the foundation for grasslands and forests. In Mars's lower gravity, trees can become very tall very fast. Their roots gather the nutrients they need and then dig deeper to turn more rocks into soil, forming a self-sustaining ecosystem. At this point, we can slowly introduce more plant varieties, insects, and animals. Not mosquitoes, though. The new biosphere needs to be maintained to prevent it from falling out of balance. If plants grow too quickly and absorb too much carbon dioxide, the planet cools down too much. If key species die out, we could see populations collapse faster than they could recover. On Earth, other species would move in to fill the void, but our Martian biosphere is not as flexible. It takes hundreds, if not thousands of years before Mars becomes a stable environment. But eventually, the planet will have the potential to sustain large human colonies. With air, water, and food available, we can finally call Mars, black, blue, and green, our home. A giant volcanic island in space. Will it last, though? Challenge 3, the long-term future. There is a problem we haven't addressed. Mars's core does not produce a magnetic field, so it doesn't have enough protection from solar radiation or cosmic rays. This becomes dangerous for the long-term health of Martian populations. So, as a final step, we need an artificial magnetic field. It doesn't have to be huge like Earth's, it just needs to deflect the solar wind enough so that it doesn't touch Mars. The easiest way is to construct a magnetic umbrella far ahead of Mars that splashes the solar wind to the sides. A big superconducting ring powered by nuclear facilities is all it takes. It would orbit at the Mars-Sun L1 point, keeping it constantly in between the Sun and Mars and protect the new atmosphere. And that's it. Terraforming Mars would take some work, hefty resources, and probably a century or 10, but it would be the first time we've lived in a home designed and shaped solely by us and for us. A first step towards our future among the stars. The first step that we can already take down here on Earth is learning more about the physics and biology needed for such a project. To help you with that, we've created a series of lessons to build your fundamental understanding of these topics. Made in collaboration with our friends at Brilliant.org, these lessons give you a deeper understanding of the topics from our most popular videos, from supervolcanoes to black holes to climate science. Brilliant is an interactive learning tool that makes maths, science and computer science accessible with a hands-on approach. Because we know that to really learn something, you've got to do it. Think of each lesson as a one-on-one tutoring version of a Kurzgesagt video. In our latest lesson, you'll learn more about how Mars lost its atmosphere and how we might protect a terraformed Mars from suffering the same fate. Brilliant has thousands of lessons to explore, from maths-based topics like algebra and probability to the concepts behind algorithms and machine learning. And with new lessons added each month, including ones from Kurzgesagt, you'll always find something fascinating to learn. To get hands-on with Kurzgesagt lessons and explore everything Brilliant has to offer, go to brilliant.org/nutshell and sign up for free today. There's even an extra perk for Kurzgesagt viewers. The first 200 people to use the link get 20% off their annual membership, which